Yeah, we're just about to dive into global positioning systems. Okay, you good? Very good. We talked about antennas and glide slope and there we go. We talked about the glide slope, and then this is what it looks like on the insulin plate. Okay. GPS. GPS actually was originally based on a much earlier system called Loran, where we knew that that the timing sequence of, or the distance of time between frequency components would change over distance. And if you could measure that change, and very small amounts, but if you could measure it, if you had something sensitive enough to measure that, you could tell how far away a transmitter was from a receiver with some degree of accuracy. And so in the old Loran days, we did that. There was quite a bit of interference because we were doing ground-based to ground-based, which meant you could get all kinds of echoes, a bunch of different problems that would ultimately interfere with this, what we're going to call a form of Doppler effect. So we then got the bright idea of saying, well, let's throw some satellites up in space, and if we throw enough of them up there, at any point in time, you'll always be within straight line distance, some reasonable straight line distance of, several hundred miles, maybe 300 or 400 tops miles of 3 or more of the satellites. Now, one of the things they originally did is they said, well, let's see if we can do this for the United States. And very quickly realized, yeah, no, it's only going to work if we do it for the entire planet, which meant that, the U.S. was paying for this thing and others could use it. That in and of itself was okay, well, so what? But it works for us and all of our ships and planes and everybody navigating all over the world. It's still a good thing for us. However, one of the things that they knew was that this was going to be a fairly accurate system. And the one thing we did not want, we don't mind people borrowing it, using it, and having a good time, except and with the exception of those who are our enemies. Okay, we don't want our enemies to be able to use this. Okay, so over time they came up with a variety of different strategies. And in some cases, those strategies required the satellites to be different. So we're actually, I think, in generation 3 satellites right now. Now they're expensive to put up there, really, really expensive to put up there, especially times 32. I think originally there were 24 in the Gen 1, then they went to 28 Gen 2, and then 32. However, you really only need, I think it's 16 to 18 to have reasonable world coverage. So there's an ebb and a flow. And in fact, when I was looking this up, there was 31 of them were active, even though the system designed around 32. Now, one of the problems with the way these things work, and we'll talk about it, is you kind of got to know exactly where the satellite is. I mean, exactly where the satellite is. I mean, precisely within a few millimeters. You need to know exactly where the satellite is. Okay, well, that's kind of difficult. I mean, throw a rock up into space, 400 miles up into space, right? Where is it? Give or take a few millimeters. I can tell you where it is, give or take a few hundred miles. Right? It's about right there, Okay, but to be able to tell you where it is exactly, it's a little bit difficult. So one of the things that we can do, and first gen didn't do this well, but the second gen and now third gen does it quite well, is we can reference these devices or these satellites to ground-based stations where we know exactly where they are down to, the micrometer. So in doing that, the GPS data that we can get can be remarkably precise. Now, I actually got to play with one of the military units, Gen 1 units, right before the first Gulf War. And it was, I could stand in the building, okay, satellite in the building with one of those receivers, start moving forward, and it would immediately start showing 2.2, 2.3 miles an hour as I sped up. If I stepped up here and did that, it would show the 2 feet increase. It was phenomenally accurate. That was old world technology. Of course, along came a conflict and a war, and one of the things the military had to do is they had to say, all right, well, we don't want the enemy using this. So we got to skew all the data and make it all wrong so the enemy can't use it. Well, then they started thinking about it and said, no, wait a minute here. We're going to skew the data. We should skew it in a way that we know what it is so we can unskew it for our units. Okay? But the other thing is, we don't want to just turn it off. We want to skew the data so that the enemy thinks it's right. So every time they fire a missile, it goes to the wrong place. In fact, it goes back and blows themselves up, if at all possible, right? So Generation 2 and Generation 3, the Generation 2, they got highly functional at skewing it. And in Gen 3, they can actually skew specific, fairly narrow regions. They can say, we're in a conflict right now, in Afghanistan. So we can start distorting the data, and we can distort it and change the distortion moment by moment. Okay? As long as you have a way of communicating to all of your local users, all the good guys, what the skew values are, so that their information is correct. So the other thing that was important is one of the things that happens with a lot of the technology like transponders is it's user, what do I want to say, user sender dependent. The transponder radar paints the transponder, and the transponder sends something back to the radar. So if I've got 1 million units out there on the radar screen is going to get, way too much. So the radar can only handle so many users. Well, one of the things we figured out fairly early on was airplanes aren't the only ones that want to use this. Ships want to use it. In fact, every hiker and every hiker's mothers, uncles, whatever, all want to have their own. In fact, every iPhone, in fact, every device out there. It doesn't matter if it's an electric napkin holder. They want a GPS in it, right? So very quickly they had to realize that the satellites can't handle that kind of bandwidth. So it's got to be whatever's happening, it's got to be the satellites and ground stations are sending out data that anybody can use to get a pretty exact location of where they are, but the satellite doesn't have to do anything for that passive user to use it. Okay. So there's actually a couple of frequencies, and we'll primarily talk about the L1 frequency. They have several frequency options for different users. But for us, there's a couple of things that have to be sent out. The first thing is going to be a heartbeat time that allows the receiver and the satellite to be in exact sync. Because remember, you're moving, the satellite's moving, the Earth is moving, everything's moving. So you've got, and so whatever we're going to do in terms of measuring my physical distance from that satellite, I've got to know exactly where that satellite is at an exact and precise time. So the very first thing the receiver does when it comes on is it's got to hear that heartbeat, and that heartbeat is going to tell it exactly what time it is. Okay? So we're all going to sync our clocks, right? It's like the mission. We're all going to sync our clocks. It's now, 16:43. Oh, by the way, there's another user. That clock, guess what it does? It listens to GPS data to get the time. Many clocks. Your iPhones, all your phones, cell phones, they all get their data from the GPS system, their time data from the GPS system. So the problem with data as it reflects to some value of information is time is kind of a funky, yucky piece of information. Okay, you got years, and years have 12 months, but none of the months are the same length. And then you got these months in there, and they're all different lengths. And then within each month, you've got days, and even the days sometimes are a little bit different. And every once in a while, we throw an extra day in there for the year, or the month, or the something. It's all really confusing, right? Okay. So what they said is, yeah, that makes for terrible data. So what we're going to do is we're going to say there are X number of seconds have occurred. Well, X number of seconds have occurred from when? Well, in the early computing days, and this is actually dates back to Unix, they started out with, they actually went instead of X every second, they said every 60th of a second. And then they said that the beginning of time, since there really aren't any computers before 1971, in any grand sense, we're going to say January 1st, 1971. Well, people started using that value, and then fairly quickly they realized that because of the amount of data information, it works out to, within a 32-bit register, you would run out of numbers. I think it was 8.93 years. So they fairly quickly said, no, wait a minute, let's call it every second. We'll mark every second and call that a data unit. We're not going to measure, we'll measure very precisely exactly when the second changes to the next one. However, at the same time, let's also kick our epoch time, the term for that is our epoch time, the beginning of epoch time, back to the beginning of the decade. So they went to January 1st, at 12 midnight, UTC, Universal Time Code, January 1st, 1970. That'll carry us out to, I think, like 2063 or something like that, before you end up having to use more than one 32-bit register to define a quantity of time. Okay, and it's just straight, flat, binary numeric number. Okay, well, that's easy. Being able to do that, that's a real easy thing to transmit on a data stream. So the first thing your receiver is going to do is going to listen to that heartbeat and say, okay, click, boom, click, boom. I know I'm X number of seconds from the epoch time, blah, blah, blah. We're now in sync. Okay? It's then going to have to send some information about itself to the receiver. Okay? It's going to have to send some information about the receiver. Now, the epoch time and the heartbeat are going to be two different values unless the GPS antenna or the transmitter and the receiver are right next to each other. Okay? So the epoch time is this is the value, both at the exact same time, both are in sync. The heartbeat gets transmitted and it takes a while at the speed of light to get to the receiver. So the difference between the heartbeat and the epic time, okay, the epic time will get there, well, you know, in other words, I'm counting 1, 2, 3, and I'm synced in heartbeat 4, 5, 6, 7, and my heartbeat gets there. Okay, I've now had 7 seconds since the heartbeat got there. That means, do a little bit of math, the satellite is exactly 972.3127854 miles away from me in a straight line distance, and I know exactly where it is, so I know how far away I am. Now, if I get a second satellite and a third satellite, I can tell you exactly where I am relative to this system of satellites. Okay? The data from the satellite is going to have been quantified relative to the ground-based station. So that then connects you relative to planet Earth. Now, this system is extremely accurate if we're going to do it based upon a known reference. So, for example, if I put a GPS antenna in one wing and a GPS antenna in the other wing, out in the wingtip, they'll be accurate to way less than a millimeter relative to each other. So I could use those as autopilot sensors. And as the plane starts to tilt, the difference would become immediately known. I know a couple of guys that have designed autopilot systems doing it that way. Okay. So the selective accuracy, again, is no longer necessary. So you'd have periods where it's only accurate to 60 meters or 300 meters or down to 3 meters, or depending on what was happening, because they basically had to do the whole system. Now the military, or I'm sure anywhere near Washington, D.C., or any other highly secure area, they can regionally scramble, and again, they can fully scramble it to where you get no GPS reception at all, or take it all the way through to where you think you're getting good data, but it's skewed, and everything you're doing is 100 meters to the left, right? Or wherever they want it to go. Probably changing. So for many years, and I think there's really several things going on, we've had these GPS systems doing pretty good. Doing pretty good for quite a while, except we already had all these other navigational systems in airplanes. So this is a pretty good system, though. It's kind of better. Does a pretty good job of getting you a lot more accurate than anything else. And in fact, I don't have to know that much. It'll tell me, just give me the coordinates right there. In fact, I could just lay that out on a screen that displays the map and put me right on that map. And man, this is great. Okay. The problem was there were a number of things that could still interfere with it. Not only the military, but solar flares, other natural, nature-based events that can interfere with it. To the degree that one of the problems is if a satellite is getting, if the receiver is getting marginal data from a satellite, you have to have some way of error checking, of being able to say, this is erroneous, and now I've got a protocol for saying this is erroneous. Stop using the data. Okay? That was not programmed in until we got into Gen 3. And we came up with this rather bizarre wide area augmentation, which what it really was a whole set of protocols and system for the GPS to be able to self-monitor, and then your receivers to self-monitor based upon that data stream, and know that that either the data it's getting is incorrect from the satellite, or there is a mismatch between where it thinks it is relative to one satellite, or maybe 3 satellites, and then the other 2, there's a mismatch. Somehow or another, it can start saying there's an error and give you some fair warning for that. However, if you're not getting that error, you can then get this thing to be pretty darn accurate. Essentially, 15 meters, if you've got 6 satellites, 15 meters, general sort of wag in there, and if you've got wide area augmentation or WASP, it'll be within 3 meters. No matter where you are. Accurate within 3 meters, 3-dimensionally.
Oh, really?
Yeah.
How come aircraft GPS, even if there are some of them are WASP, like the old 396s, your vertical is way off? Is there a lag or?
Again, they probably weren't true WASP.
Oh, really?
True WASP, if it's true WASP with full augmentation, let me frame it to you this way. Like the Garmin 430, 530, series, etc., that have true WASP augmentation, they will have GPS-based procedure holds that the non-WASP can't do because of that altitude problem. So it fly the pattern just fine, but it may wander in altitude. These guys, if it's true WASP, wide area augmentation system, it'll hold it on course, doing your 3-minute turns and 1-minute legs. It'll nail it plus or minus 3 meters. Now, I have to tell you, I've used numerous times. I've used the autopilot and GPS non-WASP and let it fly the approach up until the point that I'm flaring. Just let it fly the approach up to the point that I'm flaring, and the tail wheel might be, 3 or 4 inches off the center line. I've done that many, many times, and it's just like, it's scary how accurate it is. So one of the things that's a real problem is your receiver needs to know all the data that's available about all 32 satellites. And that data has to be transmitted, and it changes. We have errors. Sometimes we have to redirect a satellite. Other errors accrue because of orbit decay, etc., that then have to be compensated for. And so this data set, or the almanac, has to be corrected and updated. That's why when you have a GPS unit, and it's brand spanking new, and it got shipped from Pennsylvania or some other place, right? When it was built and tested. When it came on back there, it listened to other satellites, and then it sat in the box for 3 or 4 months. And then it came to you, and you turned it on and started listening to the satellites, and it's like, okay, I don't have the data for the satellites I've got, so I've got to sit around and wait until the almanac is transmitted. So the full almanac is transmitted every 750 seconds. So whenever we don't know where the current satellites that you're listening to that are important to you sit within that 750-second window. Now, I know where the ones I'm always are, because Murphy applies to me. They're always right at the very end of the 750 seconds, right? You have to wait all that time. But, so that's why if the satellites, or if a receiver's been off for a long time, or greatly moved from the last time it was turned on, you turn it on and it takes a while to acquire satellites. What it's doing, it finds the satellite immediately. Yeah, it's right there, I got it. But it's waiting for the data it needs to come scrolling around on the almanac update, okay? And then once it comes around, it's okay, now I know, now I not only do I have that satellite in terms of reception, but I know exactly where it is, okay? Got my heartbeat, I'm getting the heartbeat from it, I know exactly where it is, and I have my epic time synced. Now I can start using it. On to the next one, right? Okay, and a good GPS unit, an aviation-based unit, it won't even talk to you on 2 satellites. At 3, it'll say, yeah, we're gonna let you play, but no, this data isn't any good. Okay, and then the screen might even do something with the screen. Once you start hitting 4 and 5 satellites, it then starts saying, okay, we're gonna give you 2-dimensional data that is known to be good. And then you get up to 5 and 6 satellites, say, all right, now we're giving you 3. So it takes a while. As it's transmitting, typically you're going to see about 30 seconds per satellite, and then some break period, a little bit of break in a intersection between them. All right. So, and again, not universally reliable. Electric storms can interfere with them a little bit. Solar flares definitely can interfere. I mean, any kind of outer atmosphere distortions that are going on. Ionic sphere starts getting really weird. So the end result is GPS is kind of like anything else. You're gonna need other systems, just to be redundant. So another very common one that's been around for a long time and is getting better and better and better is called inertial navigation. Now, inertial navigation started with, we can take a piece of metal, put it on some really, really sophisticated bearings, get it spun up to a very, very high RPM, and it'll hold its relative position to the planet. As long as I don't move it, it'll stay right there. If I start to move it, it'll start behaving, flexing and moving and doing things, such that I can measure that movement and know exactly which way I went. And as long as I'm counting my time well, I can say I went to the left at this rate of speed for this distance, I must be over there. These inertial nav units are so effective, we can put them inside the head of an oil drill, a big huge oil drill, grinding and cutting and spinning around with an inertial nav sensor in it. Drill down over there, come back up to Siberia, start stealing oil from the Ruskies. Okay? They'd stay erect for 8, 10, 12 months and still retain millimeter accuracy, really, really high accuracy. Well, one of the things that's happened in this technology, inertial nav, is we don't need to have a big object spinning. We can do this with an integrated circuit and a very small microscopic object like an atom spinning and use that as our inertial nav sensor. Now you got something that not only is spinning a whole lot faster, but it's way, way more sensitive. The bigger problem with the new inertial nav sensors is they're too sensitive. You've actually got to do a whole bunch of math to scale them back down for our use. So, but anyway, so wide area augmentation, it was, it's basically what we did, and there's about 4 components to it. One of it was error checking, huge thing about error checking. The other thing was throw out a bunch of basically the same thing as a GPS satellite, only it's on the ground. And it's on the ground at a benchmark where we know exactly where that benchmark is. Okay? So now I know exactly where that benchmark is. And I'm listening to the satellite, and I think it's right there, but I know exactly where the benchmark is. And I'm seeing just a little bit of error based upon where I think I am relative to the benchmark based upon my relationship to the satellite. There's just a little bit of error. Okay, that's fine, then I'm going to correct. I'm going to include that in my data set and correct. So everything that's coming from this satellite, I'm going to correct it a little bit based on that ground reference station. Right? Again, the downside of this system is it's ground-based. Okay, all of this is happening at fairly high frequency, 978, actually basically 900 megahertz up to about 1200 megahertz. Okay? We know as we go up in higher frequency, doesn't our range get shorter and shorter and shorter? Okay? 1000 megahertz, okay, that's pretty high frequency. Its range isn't that great. So if I want to make ground stations that are necessary to my operation, they're not going to have very good range. Well, that means I just need to make a few more of them. And in truth, it's not going to work that well for us on the ground. It's not going to do too much for us. So we're not going to use this system for ground-based navigation. We'll use it for aviation navigation because as I go up in altitude, I get above the curvature of the Earth, right? And now I have straight line on a much wider window. You and I standing on the planet's surface, how far can we see before we get to the edge of the horizon? They go down to the beach and stand there. You're going to see, you're seeing about 3 miles, somewhere in there. Not too much. They go up 1,000 feet, man, you're seeing a whole lot more. Go up 10,000 feet, you're now seeing the curvature of the Earth quite well. And you're seeing hundreds of miles. So based on that wide area augmentation system, one of the problems with it, one of the flaws or potential downsides to wide area augmentation is the closer you get to the ground, the less reliable the data is from your ground-based systems. So direct receiving from the ground-based systems is problematic. However, if the satellites are direct receiving from the ground-based systems and then error checking and then correcting their errors and kicking that to you, then you're going to get the error correction already included. The only downside is the error correction is only going to occur whenever it transmits that data in the L1 data stream. Okay? If I happen to be, it decides, oh, there's an error, we need to correct it. It's a several meter error, and I happen to be in the middle of the approach, I may not get my almanac updated until after I've, missed the runway. So because of this, there's been some resistance to just say, wow, this works so well, turn it on and turn all the other stuff off. Okay. The upside of this is all other navigational systems are based upon a bearing and some distance, or the crisscross of 2 other bearings. GPS this is exactly where you are in a 3-dimensional model. Okay, so if we can make that work, it's far, far more not only accurate, but far easier to understand for any computing system or for any user. Of course, as we automated things, we also came up with a form of mass manufacturing. Then they came up with these antennas. As far as I know, although I've seen some vernacular that was used incorrectly, all of these little hockey puck antennas, they are not passive antennas. They're active antennas. Even though there's only one little connector that hooks up, there's an electronic circuit in there. Okay, so the data that's coming, or the coax cable that's connected to that is sending a small amount of voltage and ground up to there, and then the hockey puck is influencing that by transmitting data back down over that voltage. Okay, but it's using that voltage to power itself up. And it's actually got its own little computer in there, as well as all the antennas, etc. Now, of course, there's more than one manufacturer of all this. Initially, all of these little hockey pucks, although they were sold by Rami or a bunch of other companies, they were all made by Garmin, under the Garmin, and at least for aviation. I think now there are some out there that are being made by other companies, but originally when these were first made and sold on the first Gen 1 units, they were only $35. So it was like, why reinvent that? If I'm making my own GPS, I'm king or whatever. I'm just going to call it Garmin. Can you sell me 20,000 units at $30 a piece, and I'll put my own sticker on there? Sure. Garmin's like, yeah, we'll make money off of that. Speaking of Garmin. Now, a couple of things happened as this technology developed. It got so accurate with the moving map display that we created some standards. One of them is the magenta line. And the magenta line created a lot of problems for us, because it was so convenient to fly the magenta line that you get pretty complacent. Okay, there's actually a great, it's like a 1-hour documentary called "The Children of the Magenta," and it really it's about commercial airline pilots, you know, and the industry realizing, okay, there's a huge complacency problem with all of this, and obviously, what's one of the more extreme recent examples of this? Was it Asiana Airlines and the SFO? Okay, they were flying the Magenta line, and the pilot had no clue that they'd gotten the plane so slow that it couldn't fly anymore. Absolutely no clue. He was not trained well enough to recognize the signs. By the time he realized it, 2 blocked the throttles, tried to go, the plane was just in full stall right into the ground. Amazing, only one person got killed in that accident, and they were killed by getting run over by a fire truck.
They're buried in the foam, weren't they?
Yeah. Well, they may have already been dead, but
They were deader.
they were dead or yeah. Okay, so I found this cool gift. So as the satellites are buzzing around, and the Earth is spinning around, and everything's going around, and you're going from California to Oregon or wherever they're going, okay, the satellites you can see are going to change some over time. Right? So ultimately, you're going to need, and it's showing you how many satellites are actually visible, ultimately, you're going to need data about all 32 of the satellites. Right? You might not for the first couple hours of flight or whatever you're doing, but ultimately over time, over a 24-hour period, you're going to need a whole lot of data about all of the satellites.
Do the satellites, in order to prevent from colliding into each other, do they use their own GPS to make sure they don't hit each other, or how does that work?
So, I think right now there are 46,000 objects, tracked objects around the planet, flying around right now. Those are the ones that haven't already collided and broken up into a bunch of smaller objects. We track something like 500,000 objects at all time, and that's there's a specified, it's a speed and physical size. However, in terms of active objects that we know about, either still on or turned off, but big enough to be, to be a meteor or damage anything else, it's about 46,000 or something like that, different objects in space flying around that we've thrown up there, buzzing around. So each one of those orbits are tracked. And the reason they have fuel on every satellite out there is for the purpose of being able to say, okay, 3 days, 7 hours, 22 minutes, we're going to run into that object. And that object already ran out of fuel. We're just waiting for it to decay in its orbit and burn up. But it's not going to happen before we get there. So we need to turn a little bit, go up or miss it somehow. Okay. Thank God somebody figured out all this stuff about physics, right? So they can map all this stuff out with a very high degree of precision. And even then, we still have mistakes, near misses, where things go by each other, and there's enough of a gravitational pull to change courses on something, or actual impact, and things get destroyed. It still happens. All right, so distance measuring equipment is kind of an old gen technology. GPS can give it to you. I know where the airport is. I know where I'm at. Plug it in, flight plan, says I'm 6.9 miles away. So when you go in and you tell you file your flight plan, you tell them, hey, I got distance measuring equipment. I got this GPS on board. No. Now, your GPS is far more accurate than distance measuring equipment, but distance measuring equipment was technology that predated GPS, and it was kind of useful. So, for example, this would essentially send a pulse pair, and that pulse pair would separate. It did require a transmission back. So only so many airplanes could be talking to this thing at once, this particular ground station. It would measure the separation going 50-second microsecond delay in the middle, and then pop the signal back, measure up all that time, and you know where you are relative to the ground station, give or take a few meters, a couple hundred meters. If I wanted to fly let's say the runway's here, and my final approach fix is over here, okay? And I'm over here, right? What I could do is I could say, I know what that line is. That's a vector, right? That's some heading. Runway, I don't know, 19, let's say. That's a heading. I've got a VOR station there. I got a bunch of airplanes here, so I don't want to be over there anyways. What I could do is I could say, I know what my DME distance is here. So I'm going to fly staying that exact same distance. So I'm just going to fly that exact same distance. And that'll put me right there. Okay? And then as the VOR needle starts coming in, okay, I know I'm about to turn, so I'm going to anticipate the turn. Needle starts coming in, start my turn a little bit early, and I end up right there, or maybe a little bit outboard of it, pass through the final approach fix, or the initial approach fix, okay, and then that puts me right on the approach. So what you'll commonly hear is a DME arc, flying the DME arc, and a lot of approaches were set up around being able to do that. So you're coming in to let's say you're coming into San Diego Lindbergh. They might have you go out to Santa Catalina and then come in and report to some spot over there based upon a VOR intersection, okay? And that's this spot right here. Then the approach would say fly a DME arc of 47 miles out to the final approach fix, okay? And that's the map to get to San Diego. I don't know if they actually have a DME arc for Lindbergh, but so the VOR system and DME and RNAV was all somewhat dependent upon a map of a bunch of airborne highways. You fly from here to there, to there, to there, to there, based upon timing, distance, and vectors. And it'll work as long as everybody does that, right? GPS throws all that out the window. I don't need to do all that. I'm here, straight line to there. Ain't it grand? And I got some guy on radar watching me so he can keep other airplanes away from me. And so GPS kind of made a lot of this redundant. However, this works regardless of what the sun is doing. VORs tend to work, continue working, so it's still fairly useful. The systems are still out there and they're still very usable. All right, the transponder. A lot to say about this nightmare. So it turns out that contrary to the incredible top secret nature of radar, which, you know, during World War II, wow, it was so top secret that even those people that had it that were using it didn't know what it meant or how to use it or what to do with it. And I'm sure many of you have heard the invasion into Pearl Harbor was completely seen on radar. Absolutely, radar observers saw it. They didn't know what to do with the information. They tried to say something about it. People up above were like, what the hell could you know that? That can't possibly be. Oh yeah. I mean, there's a whole bunch of stuff about this early on. We were a little too top secret about it. Well, it turns out radar sucks. It's really not that good, particularly if you're low. Okay, you got any mountains around? I fire out a radar, it goes ping, poof, 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 poof. This pulse goes out and it hits stuff. And that goes back, ping, 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 back. Okay? And that works great if you're right there and there's nothing near you. However, if you're down low, and now I got Wexman and Dudes and Noonan, I'm trying to ping off for Herbiview, ping, 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 ping. Whoa, on my screen, I get a whole bunch of, man, I got 39 airplanes out there. Okay? And he goes a little bit lower, right? Now he's among the wave tops. Okay? The other thing that can happen, and actually I've had this happen offshore, back when I was doing a lot of ocean stuff. If you get near something fairly big, like a ship, all of a sudden that reflection back is so big it overwhelms the unit, and suddenly it's like you're in the middle of the ship. Everything just starts painting. When that happens, it's like if you had a little bit of a window as it started to cascade, you could tell what direction the steel wall that you were heading at was coming from, and just turn away from it. But generally it was about 2 or 3 sweeps and all of a sudden everything would go white on you. So if you saw it initially, and by this I mean you're in the fog, it's night, and you're 40 feet away from a ship, and you really, 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 really need to turn now, radar will suddenly do that. Well, guess what? Radar sucks, even up in the air. Up in the air, we kind of do some things. One of the things that's kind of deal with that I can do is I can come over here, and now when I paint you guys, I see you just fine, right? The other thing I can do is say, well, I got a bunch of mountains here. I know you're going to be up there, so we'll just sort of lift our initial. Okay, remember we said we could shape antennas like a Yagi? Well, we'll take that antenna and lift it up so it only shoots up. Okay, now most of the energy of the reflection is going to go up that way, but we'll get enough back down here to where we can use that, right? And the higher up you are, the better the radar return will be. But it kind of sucks. So what they said was, well, look, in these high density areas where we've got a lot of airplanes, let's just put a little device on there, and it's a transceiver. When that transceiver receives the radar blip, ka-ping, it goes kapow and transmits something. Just transmits a boing back. Okay? So now, rather than waiting on reflected energy, I'm going to get an actual transmission coming back that's going to show up on the radar very, very clearly, loudly. So loud, in fact, that I can turn my radar sensitivity way down, tune out all the other stuff, and I know exactly who's there and where they are. Well, I don't necessarily know who they are. Well, that's okay. We can figure out who they are. We'll have them not only be able to transmit a poing, but we'll have them transmit some unique identifier, some code that lets me know who they are. Okay? Well, that'll make life a whole lot better. This would be great. It's gonna be grand. Only we're gonna have to mandate it, and these things aren't cheap, so we're gonna mandate it only in those areas where there's a lot of radar, there's a lot of traffic. So pretty much all the big airports. Right? So then we came up with terminal control areas, TCAs. And then we also came up with, what is it, active radar service area, I think it was, ARSAs. And then they had terminal radar service areas, TARSAs. And then they had well, finally there was sort of a really nasty accident. It happened to actually crash right into North Park. A Boeing 727 being flown by 4 PSA pilots, actually 3 PSA pilots and 1 FAA check ride individual. And they ran into another airplane. Cessna 182, I think it was. That caused everybody to realize, we got some real problems here because we have so many of these areas. We're going to consolidate any of these radar services into one, because a big part of what happened is they were on Miramar's radar services, got handed over. They were a company in San Diego, it was PSA, so they were used to taking a shortcut and abbreviating the approach. And then they didn't see the airplane they ran into. It went right across their screen all the way. They looked south and saw an airplane, thought that was it. They got told about it, thought that was it. Turned out that was down over Southwestern College. They never saw the plane they hit. But a big part of the crash occurred because we had all these radar services too close to each other. So that's when we came back through and eliminated all of that. And we now have Class B airspace, Class C airspace, which was the TCAs, the ARSAs. Class D is all your airport terminal area. Where you have a control tower, those usually have some form of radar service, or at least radar perspective for the controllers. And then anything above 18,000 feet, you will be on radar, period. That means you got to have one of these. So any place that we have a Class Charlie, a Class Bravo, or above 18,000 feet, you got to have one of these puppies. So that kind of has been in effect. Well, it's been in effect since the mid-60s, and then we went to the alphanumeric class. I'm going to say that was about 85, 88, somewhere in there, something like that. I don't remember exactly. So it turns out we're at fairly high frequency, kind of the same with GPS, fairly high frequency. That means we got a really short little antenna. That's longer than the actual antenna. Antennas actually only needs to be about that long. It's a little bitty dinky thing. Because it's so short, it's probably not a good idea to put it up on top of the airplane because the curvature of the airplane is going to blanket a little bit. So we're going to have to put this down under the belly. And they have a variety of different kinds of antenna. That's the low end one. So this transceiver says, I got a radar blip. Ba-ding! Kapow! I'm going to send some data back. So if I don't have a transponder, what the radar service will get is what's called a primary return, and it'll be just a little blip on the operator's screen, a little blip. If it's got an enhanced primary return, then there'll be a numeric value. Because the bandwidth was so bad when we invented these things, we didn't really have room to go from 0 to 9. So what we did is we went from 0 to 7. Okay? And we said any one of these 4 digits could be a 0, 1, 2, 3, 4, 5, 6, 7. In doing that, they came fairly quickly realized that if I had a whole bunch of airplanes flying around, I'm still going to kind of may run out of bandwidth. But more importantly, there's a whole bunch of airplanes I don't really care about. I need to know they're there, but I'm not dealing with them uniquely. Okay? So I'm not in what's called a positive control relationship with them. So what I'm going to do with those guys, I'm going to say, because we've already got this thing called instrument flight rules, okay, and visual flight rules. So what I'm going to say is anybody that's operating under visual flight rules and is not receiving any radar services, we're all just going to put them on a common number, 1200. Okay? And that way, any radar that's painting them is going to say, oh, I got a 1200 there. That means they're visual flight rules and nobody's talking to them. And they're not talking to anyone. Okay. As long as they don't fly into the wrong airspace, that's okay. I know they're there and I know kind of approximately what they're doing because I can see what they're blipping along. Okay? So that eliminates a whole bunch of other things. Well, the other thing they did is they said, look, in Southern California, I got 3,000 airplanes flying around, or whatever it is. It's not, but it's probably, at any one time, middle of the day on a Saturday, it might be 300 airplanes flying around. Okay, that's a lot of work for one person. So they divide this all the airspace up into a bunch of smaller areas, and each controller is given an area to take charge of, and they might be handling anywhere from 1 to 15, 18 airplanes. Okay, and of course, as the airplanes are moving along, they're handing them off to other controllers via different frequencies. Meanwhile, rather than give everybody a unique code, they might do some things like, let's say I'm responsible for my airport traffic area. And most of the airplanes I don't have to worry about too much. But I've got some that I need to worry about a little bit. So for my airport traffic area, I might be given a code, 0212. Okay? So anybody that I'm going to put on radar services, I'll put them on 0212. Right? Squawk 0212. Tell them to do that. That way, any of the radar services out there know that's my airplane in my airport traffic area. And as they flip to a new, go into a new area, they may not only give them a new radio frequency to talk to, but once they get to the new area, they may give them a different squawk code. Okay? Now, of course, what happened is, remember, this is overlaid over all these canned navigational routes. So what they then did is they assigned squawk codes to each of these canned routes. So they said, if you're doing the Santa Catalina Star from Lindbergh to, up to Sacramento, these are the standard codes we're going to give you. And anybody that's displaying that code, we know exactly what they're doing and where they're going. Okay, so we had some okay work with this, but the radar isn't very accurate. Well, that's okay. If it's not very accurate, we know what its inaccuracy is, so we just skew everything for that area. The problem is, not only is it not inaccurate, but its inaccuracy isn't consistent. So there are areas, in fact, part of what may have happened with Malaysia Airlines is there's several areas that plane was flying through where we know there are huge radar inaccuracies because of echoing and reflections. So the other thing they did is they saved a couple of frequencies up there, and I don't remember, one's hijack, one is you're screwed no matter what. I think 77 says everything sucks. 75 is hijacking, and 76 is radio.
76 is communication.
Yeah, 76 is your radio doesn't work. Hopefully the transponder does. I think 7500 is we're being hijacked. And 77 is help, help, Mr. Wizard, help, Mr. Wizard. All right. Okay. So along around the 80s, as we were changing into these class A, B, and C areas, actually it predated it a little bit. These secondary service radar systems were set up. And we basically said every class Charlie, Bravo, and Class A above 18,000 foot airspace. This is about 5 years before they came out with these alphanumerics. We said, you all got to be giving us more data than just this squawk code. Because the problem is we have a good idea where you are, but we have no idea how high you are. And we've got so many airplanes, we need to start separating them. Okay? So we can have a big pancake of airplanes, big stack of airplanes, like a stack of pancakes. Right? So we need to know your altitude. They then said for any one of these areas, okay, Lindbergh or Class C John Wayne or Boise or Portland, LAX Class B, San Francisco Class B, anything above there, we said we're going to make a 30-mile veil all the way around the airspace. 30 miles. If you're inside that 30 miles at any altitude, up to 18,000 feet, and there's a few that actually have a special ceiling that only goes upside, but if you're in that area, you must have a transponder that is on, is operating, is certified, and is giving us pressure altitude data. Now note, it's not giving us altitude, it's giving us pressure altitude. So it's giving us pressure altitude normalized to 29.92. There's going to be some errors there. Well, so what? As long as everybody has the same error, we're good to go. Okay, we'll still be 500 feet, or 1,000 feet apart, right? So with them in, that then meant everybody had to go out and buy new transponders. Well, okay, some folks had to go out and buy new ones, but other ones had already bought later, a little bit slightly later model transponders that had the option for data to be transmitted into them. However, it was really badly done. It was basically what was called gray code analog data being provided. It required, I think it was 9 communication lines. And the information was not, it wasn't serial, it wasn't digital data. It was analog data being provided to provide anywhere from 1 or 0 to 20,000 feet, or the higher altitude went from 0 to 40,000 feet encoders. Okay, these were initially kind of expensive, but they would give that pressure altitude data to the transponder. Okay, so now you got a situation where you got a transponder, a little antenna sitting there, and every 6 seconds the radar sweep comes by. It goes ping, 1200. Sweet. Ping, 1200. Okay, so it says ping, here I am, and 1200. Or whatever my unique identifier, swap code is. Now it says, sweep comes by, ping, 1262 for 6,200 feet. So it's going to be in hundreds of feet. Now the encoder data can be quite a bit more accurate than that. So all we need to do is in hundreds of feet. So ping 102, or ping 1200 102, ping 1200 230. Red flag. Why red flag? Because 230 means you're at 23,000 feet. You can't be on 1200 because that's VFR. You can't be VFR above 18,000 feet. Right? Gotta have it. Don't need any of this crap if you're more than 30 miles away from one of these secondary surveillance radar systems. Okay? I'm flying, well, Fargo, North Dakota actually has one, but I'm flying anywhere else in North Dakota, Wyoming, wherever. I don't need any of this stuff. It's only where there's a lot of airplanes. A lot of airports, a lot of airplanes. But radar sucks. Radar's kind of sucky, so guess what? Yeah, and you know, I'm sorry, but it sucks. So, no matter what we do, no matter how congested it gets, we're going to keep all the airplanes at least 4 miles apart. And at least 1,000 feet apart. Because radar sucks. As long as I'm 4 miles away, you know, plus or minus a little, okay, we're not going to hit each other. So we're going to keep any airplane on radar services, we're going to keep them 4 miles apart. And if anybody else comes in within that 4 miles, we're going to start vectoring them around. Of course, this guy probably violated the airspace. Right? So we're also going to follow them and have them shot down or arrested or whatever. Well, the problem with that is I got 9,927 airplanes flying into San Francisco, Oakland, what's the one south of there? San Leandro, and then San Jose. San Martin is another one that has an instrument approach. Okay, so I look at the Bay Area. Man, I got a zillion airports there. And all these airplanes at a whole different variety of speeds. And I got a little bit of fog going on. Okay? So now my available space, physical space to put all these airplanes on approach into San Francisco, departing out into Oakland, departing out into San Jose, departing out into the other airports, I got physical volume. It's full. It's saturated. I'm done. I can't add one more airplane until one lands. Okay, one landed, put another one in. No, you don't get to take off for a while. Okay, now we're clear, you can take off, okay? Now I'm gonna go into what's called flow control. And the only thing we can do at this point is we're gonna say, oh, you wanna take off and get into the line here, don't you? No, you gotta sit there. In fact, I got 900 other airplanes waiting to get in line. We're so backed up. So rather than having you take off and fly around for a while, wasting a bunch of gas, we're just gonna have you sit on the ground. Why take off? You're not gonna get there, okay? As long as you pulled away from the gate, you're not gonna get a violation for late flight. We had to change that rule real quick too, right? As long as you backed away from the gate in time, you're not gonna get in trouble for a late flight. You can go sit on the ramp all day long, we don't care. Okay, we don't care how annoyed your passengers get. Wouldn't it be a little bit more convenient if we could, like, instead of 4 miles, we could make it 3 miles or 2 miles? We could fit more airplanes. Make it a whole lot more convenient. Because at 4 miles, guess what? The runway doesn't get used a lot. Okay, land, taxi off. Okay, land. You know, a lot of time the runway isn't being used because the airspace can't fit more airplanes in. So yeah, there's a couple of different encoders. So I'm setting us up for the next generation of crazy to come down. Now you should know that when they invented these and started mandating these, the other thing they did is FAR 43, what is it, Appendix G or F? I can't remember. They created all the specification standards, operating parameters for what a transponder must be able to do. When you turn it on, this is what it must do, and this is what you must verify that it's doing. At the same time, they created a technical standard order and said this is how it must be built and all this stuff you do to meet this parameter. They then went over to Part 91 and said, well, basically in these different airspaces you've got to have it, and no person may operate a transponder anywhere, in your car, on the ground, in a crib with green eggs and ham. You can't use it anywhere. Cannot turn it on unless in every 24 calendar months you've done and met all of these parameters. However, when they went back and made the encoder requirement for secondary service surveillance radars, and they updated the standards for that, there was a little bit of problem with the TSO. If your unit gets painted by more than 6 different radars, it says, I've got to do what I was programmed to do, and it turns itself off. It says there's an error and turns itself off. That's the current standard today for all transponders. It turns itself off. I assure you right now, you're being painted by way more than 6 radars. Okay, it turns itself off. If you have an airplane with a transponder in it and it works, it cannot be built to the current technical standard. So this starts a huge political problem with the FAA. The FAA created the standard. They know it doesn't work. And everyone that's sort of a chosen child, like Garmin and King and Bendix King and whoever, the FAA kind of goes, well, we know it needs to work. And they want to produce them and make them work. And if we hold them hard to that TSO, it won't work. And then it's going to get really ugly because they're going to come back and say, we're taking you to court because you have the standard that doesn't work. We're going to get a lot of ugly on our face. I know all of this because I know 2 different companies, international companies that have tried to get into, that got into it. In fact, Micro built a wonderful transponder, and they couldn't, every time it got painted by more than 6 radars, it would shut down because they built it to the standard. Okay, that sets the stage for the FAA's behavior around this. They don't, it's like, don't bother me with the facts, my mind's made up. And rather than being willing to admit, oh, let's improve this, Nope, don't bother me with the facts, my mind's made up.
Why would the FAA not? Why would they do this?
Because it's an embarrassment to them. It's a huge embarrassment. They have to admit they screwed up, and then they become liable for all kinds of potential problems. I know you guys remember the value jet crash into the Everglades. That airplane was on fire on the ground, fully engaged on fire. It's irrefutable. There's no way the melting damage that could occurred to it could have occurred in the 9 minutes it was airborne. It had have to have been on fire for at least 15 minutes for that amount of damage to occur to it. The reason nobody knew is because the Class C cargo hold that was on the airplane didn't have any smoke or heat sensors in it. It wasn't required to for a small Class C cargo hold. The only country on planet Earth that doesn't require them is the United States. All the airplanes have it in the wiring harnesses. And the industry says, oh, it's going to cost us too much. All the airlines, Alaska and United and all, they all say, that's going to cost us too much. The reason the FAA isn't going to do anything about it is because there's already been 3 accidents related to that. If they come back and say, oh, we screwed up, we need to mandate that as a standard, now all the survivors from all those 3 accidents can come back, and now 4 because of value jet say, you're at fault, FAA. How much money do you think that's going to cost? Okay. This is huge. Saudi Air went through a similar thing, and once they realized, hey, wait a minute, this stuff's available, they immediately went back through, bought all the sensors, and put them on all their airplanes. The bigger Class D cargo holds, 777s, 767s, etc., they're all required to do that. The Class D, Class Charlie, which is going to be your 727s, MD-80s, Super 80s, your smaller airliners, they were never required to do that. And as far as I know, to this date, the FAA is still, we don't ever want anybody to think we're liable for this.
What's the ident feature? What is
Okay, so the ident feature on a transponder, I think I talk about it in a few slides.
okay, never mind.
Yes, I do.
Okay.
Okay. So one of the advantages of this pressure altitude thing is I've got some data. Why not display it on the screen of the transponder? If your altimeter goes belly up, hey, at least I'm getting something. Okay? And in fact, with a decent encoder, I can get really good precise data. Even though in this case, I'm only going to report a 47 to the radar provider, I can still get pretty good data, more than enough data to be able to fly that puppy and not hit the ground too hard, right? Truthfully, if you're looking at the altimeter to land the airplane, go back for some more flying lessons. So it turns out we could have a whole bunch of other things in there. Like we could put a couple of timers in there. Maybe a time until takeoff, a time till next waypoint. Might as well. It's all digital. If it's all digital, all that information's in there anyways. So let's. In fact, I think I'm going to do that because I want to sell more transponders than he does. In fact, he's my competitor. I want to beat him. Okay, so I'm going to put all kinds of whistles and bells in this thing. So not only do you have different codes that you can squawk, but we're also going to have different modes because of this history. So the first thing we're going to have is off. OFF. That's a good feature. It'll usually be on the main knob. You can also pop the circuit breaker, but OFF is a good feature. We're then going to have, and this is almost not necessary anymore, we're going to have what's called an on standby. Now, the early transponders were actually somewhat, they fired a pretty significant ping radio transmission. So they used a cathode ray tube that was very much like a microwave tube, and it took quite a while to warm up. It takes a good 10 to 15 minutes to warm up before it'll actually start transmitting correctly. We don't need that old analog technology anymore. But it used to be that you had to warm the thing up, and then there would be times in the operating environment where you didn't need the transponder transmitting, but you wanted it on so that thing stayed warmed up, right? So we've got this, and we're left with it in industry. Now, theoretically, I could just turn the darn thing off when I don't need it, and then turn it back on when I need it, and it just, it'd come right back on. Everybody's happy. Even today's new world technology, they've got off, on, standby. Now, there's been a little bit of, I've been playing around with trying to prove with the new digital ADS-B system, which I'm going to talk about here maybe when we come back from the break, whether or not on standby still transmit ADS-B data. The FAA and a number of others claim it doesn't. But I did a little bit of listening with an antenna and just my oscilloscope on a couple of different transponder ADS-B out systems, and it looked to me like, I don't know what the data was, but something was being transmitted. So I don't know. It'd be kind of interesting what's happening there. So on then just says, I'm going to do the ping, hey, I'm here, and whatever my squawk code. So ping 1200, ping 0200. Then I go on pressure altitude reporting. Now I'm going to go ping 1200, 2200. Okay, or 220, well, whatever the number is. Now I'm flying around. Mr. Wexman's flying around. Mr. Noonan's flying around. We're all flying around. We're all flying around El Capitan Reservoir. We were having a good time. One of us calls in and says, "Hey, Gillespie, how do I land?" Gillespie looks on the radar and says, "Man, there's a lot of airplanes out there flying around. Which one is it?" They're all 1200. Which one is it? He's going to say, "Could you hit the ident button?" I got it, says indent. It should say ident button. Can you hit your ident button? And what that looks like is, I think if you go back here, you see the little ident right there, IDT right there, ident. Boom. What that does is and I think it's a minute, what that does is it creates a flag. It sends ping 1252 blip. It's just enough of a blip to distinguish that one blip, and it'll show up as an IDT on their radar screen. So they'll have the airplane, a little vector, an altitude. They can actually turn on radar speed as well as altitude, and then that little IDT flag or a little flag, and that tells them which one you are. Okay. Now there's another reason they might ask you to do that. Call them up and say, "Hey, this is 9, and you grumble it real fast, because you don't want them to know who you actually are. I'm out here, I want to land." They say, "Roger that, 9. Could you hit ident?" And of course, you're okay, sure, you hit ident, it's fine. You go in, you land, you pull off the runway, they click it over the ground. The ground says, "Yeah, 9, be prepared to take down a phone number for you to call." Okay, now they've got you on tape as the person that uniquely identified coming all the way in and landing. And of course, radar has taped you all the way back to wherever you flew into Class B airspace or did some other thing that really annoyed them. Okay, so every once in a while, a controller asks you to ident. It's like, maybe I won't do that. Maybe I'll just go land somewhere and hide out. Right? Actually, I've had that happen somewhat recently. And it turned out they thought I had violated Class B airspace, but then when they went back and looked at their tapes, they were like, "Well, I have no idea why they want to talk to you." And now I was talking to the station chief over here at Traycon. He's like, "I had no idea why." I was like, "Well, I got 3 GPSs plus a sectional, and I know the airspace better than most of you guys do. I can assure you I was not in it, and I got proof." I've got a whole bunch of data logging. So if it showed me in it, you need to get your radar fixed. And he was very nice about it. So it turns out, yeah, you got to get this thing calibrated and certified up to this really crazy wonky standard. And they want it done that way. And it's got to be done that way. Now I sort of defy you to be able to say, I call them up, hey, Drake Don, I'm out here flying around and I'm at, my altimeter says I'm at 6,300 feet and I'm at this location. What do you got on your radar? Oh yeah, you're at 6,300 feet at that location. Well, how can it work any better than that? It's good to me, right? And according to the FAA, for some bizarre reason, you've got to actually take it to a radio station or to a radio repair station. They've got the transponder checked. They've got to do several things. They've got to verify that it in fact is putting out the correct data, that it's within, it's not wandering off frequency any. You've also got to verify that there are no leaks, that the system, that the altitude encoding system, the pressure altitude going to it doesn't leak, it's feeding you the wrong data. Which of course, if it was leaking significantly, you would be displaying the wrong altitude to TRACON. But you need to do that every 2 years.
That's only for an IFR too.
That's all. Well, you can't operate it if it hasn't been done. If the calibration hasn't been done every 2 years, you have to do the leak check for IFR.
Yeah, there's no leak check for VFR.
For VFR, right? You still have to do the calibration.
If it needs to be.
No, you have to have it checked every 24 calendar months.
Yeah, but most of the time you don't have to calibrate it.
But you don't have to actually change it. You just have to have a
For
measure.
VFR, you don't even need to check that it's putting out the right altitude. Just that it's transmitting.
Really? Did they change that?
That's what the regs are. You only run up and down the altitude for IFR certs.
Right, but in other words, I can't call TRACON and just ask them to give me, ask them to see me and have that qualify as a transponder check.
And there's a lot of other things you gotta look for.
Right, it's the other things you gotta look for that you gotta pay the money to have it done. And to buy the machine to do it costs more than it's worth. More than the number of times you will self-certify it every 2 years. Okay, so you gotta do it. I still think that's probably a little bit overkill. Okay, so the FAA said we want to put more airplanes into a smaller amount of airspace. Not only is the 4-mile window thing kind of a problem, the box, but the truth is we can get routes closer to each other. We can do a whole bunch of other nifty stuff. Okay, and in fact, if we made routes closer to each other, we could make more direct routes. A whole bunch of nifty stuff. If we could do this. Now recognize, once you say let's make a change, it's a national political problem. It has nothing to do with technology. It is immediately a political problem. Because you're talking about, can we actually make the technology and sell it to the customers? Over here, can we make the technology and sell it to the government and have it installed in a way that it actually works? Okay. Can we do all of this within reasonable expense to the customers, to the government, to everyone else? And of course, if we throw a mandate out there and says it's got to be done by such and such time, you know what's going to happen, right? We're all going to say, well, I don't have to worry about anything until, then. Then along about 2 months before then, everybody goes, oh man, I got to do this. Suddenly, industry needs 72,000 units. And they're putting them out at 10 a day, right? So it's been sort of a mess. Well, and guess what? The FAA, living up to its plan form of creating transponder standards that don't necessarily, that aren't functional if you build it to TSO, they've done the same thing here. They created some standards. They then found out that what we're going to try doing, we've said every time that the radar goes blip, I'm going to give you some data. 1200 altitude. Ping, 1200 altitude. Ping, 1200 altitude. But there's a long period of time in there where nothing's happening. Well, let's add some more data. Most of these airplanes flying around have a GPS on them anyway. Why not give us some GPS data? And GPS data, you can tell us exactly where you are, what your airspeed is, what your track is, vector, all the stuff about you. Let's throw it in there. Well, big brother, a unique identifier about who you are. Well, before we do that, we need to go back to the database on all the registration and create some unique identifiers. So that took them a while to do. Now, if you look up any registration, you'll have an N number. There'll also be a hexadecimal code that's unique to that airplane. You need to know that because that hexadecimal code is what you're going to plug into the ADS-B equipment for that unique airplane. Boy, howdy, Big Brother is now really going to be watching you. Well, the first thing the FAA did is they said everybody's got to do this. Only the regulation said no, only Class B, A, and C airspace. Same rule for the same transponder. Okay, so there's a lot of consternation, and people have started to figure out. And you know, if I live in Wisconsin and I never go to Green Bay, I don't need any of this stuff. Okay. If I've got an airplane that's I might want to occasionally fly over to Madison or Green Bay or something like that, then maybe I got to get the stuff. They also said, well, there's going to be a mandate, 2020, you got to get it done. I'm pretty sure they're going to find themselves in a world of hurt. Because one of the things that happened just recently is they came to the realization that it's like, wait a minute. We knew the GPS's data was problematic, so we created the wide area augmentation system. Okay, we made these TSOs and everybody came up with the stuff and we got all this great technology. Well, it turns out that how some GPS units talk to some transponders, talk to some of this new system, errors occur. So now compatibility amongst all the equipment also has to be certified. So now they're going back and making compatibility requirements. The one thing they did do that is kind of cool is once you set up the airplane for this new system, this ADS-B, and when we come back, we'll talk all about what it is. I went for a flight yesterday. I don't forget what the time limit is, but it's like a couple of weeks. If I go in and say what my N number was, and give an approximate time of the flight within an hour, about half an hour later, they'll email me a report of that flight. And it'll show me all the error checking, all the data and whether or not there were errors and all the rest of that stuff, which is pretty good feedback. What they haven't answered quite well yet is I can cause it to have errors. I can get the GPS to create all kinds of errors. All I got to do is turn the airplane upside down. There's no law that says I can't go. As long as I'm not over congested airspace or an airway, etc., I can be all day long. Their mandate kind of says it has to work, but I can do aileron rolls and generate errors all day long, and I'm not breaking any rules. And the system's working just like it's supposed to. So, again, I can go on and on and on about some of the flaws I figured out with, or the conflicts that they've come up with, that they're eventually are going to figure out our problem. The other problem that has occurred is as they figure out these problems, they've suddenly realized, oops, what we told folks, particularly the folks that have invested millions of dollars in designing and developing this equipment, is wrong, and now they're going to have to develop more. Okay? As a user, I've already had to buy a second wide area augmentation GPS puck because the error checking in the original one was wrong because the FAA changed its standard. Okay? That only cost me $530 because the FAA screwed it up. 530 times how many airplanes do we have? 500,000? Okay, so this is going to be a huge problem. Guess who's going to get beat up? It's not the FAA. They're not going to get beat up. You guys, the installers, are the ones that are going to get beat up. Okay, and you say, nothing I can do. It's red. It's, you know, here's your report. It's red. It's red because it's, the doohickey here isn't compatible with the other equipment you got. It's right there on the list. It's not my fault, but okay. or it was compatible, but now isn't because they changed the standard. Yeah, I'm kind of annoyed right now by this, but at the same time, one of my airplanes is functional with it. So when we come back, I'll start talking about, we'll talk significantly about ADS-B and how it works. There's a significant plus to it. It provides real-time traffic information displayed on the screen. It also provides real-time, almost real-time weather information. That's hugely. The radar stuff, okay. But it's really, really cool to be able to take off someplace like, let's say I take off here, and I know I'm going to San Jose, right? I can listen to the airport terminal information system for all the airports within about 30 or 50 miles of me. I can't get that same, that what we call METARs about all the other airports from far away unless I have to call somebody up. Well, with ADS-B, plunk, plunk, dial in the airport, poof, it's all displayed right there. So the airport, long before I get to that area, I know what's happening there. So there's some real significant advantages to it. And in fact, I think they really had to say, if we don't give people a carrot, we don't give them something, they're going to start doing what? Writing their legislator, saying, you're making me pay tens of thousands of dollars and I get nothing for it. Right? Okay, the FAA isn't going to do, they're not going to, no government agency is going to do anything that's going to jeopardize the funding stream. So they have to give us a carrot. I think in the grand scheme, it's going to be a good thing. For our perspective, hey, 500,000 airplanes, they all got to have it by 2020. Okay? I don't think they can build that many units by 2020. My guess is right now, just looking at what I see, probably about slightly less than a quarter of the airplanes that I see flying around Southern California have it. When you have it, it gives you information about the other airplanes, so you actually, when you see it on screen, you see their N number that you're flying along when they have it. And when they don't, it just shows the primary target as an airplane flying along in the altitude. So, all right, let's come back at, I ran a little over, so how about 20 kills?